Hello viewers, welcome back to emulating Risc-V in a high-level language. Today is the day when we finally start disassembling and emulating real Risc-V instructions. Up to this point we've been talking about preliminaries to better understand the process, but now we're actually going to implement some real Risc-V instructions. And so let's get started in this process. We have our project and we have our little test code, but before we get started on coding, we have to understand the challenge or the task that we're setting in front of ourselves. So we want to emulate a Risc-V in an instruction set. In order to do so, we have to understand what the Risc-V instructions look like. Fortunately, there's a manual that explains all this, and it's called the Risc-V Instruction Set Manual, which can be downloaded from the net. There will be a link provided. And it describes the way that the Risc-V instructions are formatted. Remember from our last session, we discussed encodings, and this is just another example of an encoding where the engineers who designed the Risc-V instruction set architecture have specified that the instructions, which are 32-bit words, have different fields, as you can see on the screen, and these different fields mean different things. They encode various things. For instance, they encode a register number here. They can encode a function or operation, and they can also encode immediate values, that is, values that are taken literally rather than referring to registers. And so one of the nice things about the Risc-V instruction set architecture is that the instruction encoding is for the most part rather simple and clean. There are a few surprises, but for the most part it's very easy to write code for decoding and encoding these words. So the challenge or the task set in front of us is to be able to both take a word like this, pick it apart into its constituent pieces, and then use those different pieces as a starting point for the emulation. Conversely, we also want to be able to take instructions that we're writing in a human readable format, our little assembler, and then use them to actually build these instructions. So we're going to do these two steps in lockstep. So let's take a look at the manual then. Here the manual describes the four principal formats that these Risc-V instructions are encoded in. They all have a common encoding part, which are the 7 lowest bits, the least significant bits, which contain the operation code or opcode, the major opcode that describes the kind of instruction this is. And the bits inside of the opcode will decide whether this is an R-type instruction, an I-type instruction, S, or U-type. An R-type instruction is an instruction that takes two registers as inputs, RS1 and RS2, and then produces an output in RD. And the bits in func3 and func7 will be used to specify more specifically which kind of operation we want to do on these registers. Is it a plus addition or subtraction, multiplication, and so on. The immediate type instruction is used when we are specifying one of the operands as an immediate value. For instance, our friend the add I instruction that we had in the previous sessions would be implemented using this particular encoding. So we have the destination register here and one source register, and then the immediate value in this 11-bit field over here. Now this S-type instruction format is used for the instructions that store values to memory. It is a little weird because what's happened here is that the 11 bits of the immediate value, which were nice and consecutive here, have been split apart into two pieces that we have to put back together again when we are decoding these instructions in order to interpret them, and also have to be split apart when we encode this in our little assembler. And then we also have the U-type instructions, which are used in some very specific instructions where the immediate field is 20 bits long rather than only 11 bits long. We'll get to these once we get started, but we're going to focus on the I-type and the R-type instructions initially. So what is an opcode then? Well, in this manual there's a handy list of instructions and their encodings. And the way this works is you look at these pieces of the instruction word to decide how to continue decoding. So the 3 bits starting at bit position 2 and continuing on to bit position 4 are the low part, and then this is the high part, the bit starting at position 5 and the bit at position 6. If you put those two together and you get 0, 0, 0, 0, 0, then that is a load instruction, and or a load, an instruction in the load group, I should say. If you instead say 0, 0, 1 and 0, 0, there's a load floating point instruction group, etc. So all of these different bit patterns mean select a particular major group of instructions. And then within each one of those major groups of instructions, if we go back to the instruction encoding, the other func3 and func7 fields will further specify within that instruction group what specific instruction we want. So let's go back then to the list of instructions, and we will see that there are quite a few nice instructions here. And some of these should look familiar to you if you've been following along. For instance, here we have a bunch of load instructions where we can load a byte, load a word, load a half word, a 16-bit quantity, and then load a byte unsigned and a load half word unsigned. And we'll get back to why the difference is here, but it should ring a bell if you remember our previous discussion about signed and unsigned numbers. And then we have the converses: store byte, store half word, store word. And here's our friend the add immediate instruction, which does so many things. And we're going to be we're going to implement the add immediate instruction first. So before we jump into this, I would like to first start off by creating some framework for working with this, because I intend to move this emulator over to the Risc-V decompiler environment or solution. I would like to start writing unit tests for the work that I'm about to do, and the payoff is that we will be running under sort of a safety or above a safety net, which will catch any regressions that we might introduce as we start developing the code. Now, in order to do that, we need to create a unit test project. So let's go ahead and do that. Actually, we can probably do it from inside of Visual Studio Code. So we'll say we'll make a directory called test, and then we will say .NET new and unit. That was easy enough. And then we go to the solution and we say .NET sln rvfun.sln add, test.cs proj. Great. So now our solution contains some tests. So let's see if we can build and run these tests. We need to build them first. Okay. So let's go back here. Okay, great. So now, with any luck, we have found our unit tests. And let's go and edit this test. So don't like the namespace. And this file, let's rename this file. Let's call it emulator tests. Great. And go. All right, so Risc-V emu add I. So we're going to write a test to emulate the add I instruction. So how do we do this? Well, the first thing we need to do is set up an environment in which this little test will run. And the environment is going to be a memory. So we'll need to create a memory. And this is a new memory. And we need to pass it a chunk of bytes. Oh, and we also need to use our namespace rvfun, which means we need to make sure that this project test includes the main project. So we've added a reference to that external project. Now let's try building, and we should be able to create a memory now. And in our unit test, we'll just use a single kilobyte of memory. And then we'll create a variable memory that we'll use for our tests. We will also create the emulator, which uses the memory chunk, and we'll make that a member variable as well. Cool. Okay. So now what we want to do is, given this chunk of memory, we want to assemble some instructions into that memory. So what we'll do is we'll create a function called run test, where we give it a function to something that accepts a assembler, which will build a test. We create an assembler, and then we will run our test builder, passing it the assembler, and then the resulting what will happen is the assembler will assemble our instructions, but instead of what it was doing before, which was creating these in-memory objects, we're actually going to create the actual bytes that need to be stored into the memory. So we're going to be changing the assembler so that rather than creating instruction objects, it will write byte patterns into our memory. Once the assembler is done, then we will start executing at a particular location. So I will say emulator exec. And by default, this will always start at the first byte. We will change this later, but for now, we're trying to keep things simple. Alright, so what else does the assembler need? Let's see. The assembler doesn't take any emulator at all. But now it probably will need to take the memory. So we'll pass in the memory. And we'll add that constructor. Now let's try building this and see if it flushes out these errors that we're seeing. There's one error. 7 problems. Okay. Okay, so the emulator, what does it need? It needs, the list of instructions is no longer going to be separate. It's going to be in memory. So we'll remove that argument from the emulator. We'll remove the program as well. And there will be errors now, so we'll just comment out this code for the time being. And then we will no longer need to do this. This is just our main program. We can get rid of all of this code now. And let's try building this. Great. Okay, so we're building, but clearly not working yet. So the idea is now that when I write one of my tests, I will say run test, and I will pass in a little test which will use the assembler to assemble an instruction. So I will say something like m.assemble, and then we'll use our add I, and we'll use register 2, and we'll take the value in register 2. Actually, let's take the value in register 0 and then add the number 42 to that. So if we run this, then we expect that the register in the emulator after the execution should contain the value 42. So what we'll do is we'll verify this by using an assertion, and we'll assert that the emulator register 2 has the value 42. Great. So we need a reference to add I. So we'll use and this was called mnemonics. Like that. Cool. So we have a compiling unit test, but nothing's working because we have to get the assembler to work in this new way. So rather than assembling into a list of instructions, we're now going to assemble into memory. So let's take a look then at what the assembler now needs to do. So when we ask it to assemble the add I instruction, this assembler function has to look at that and decide, oh, this is an instruction of the I type. So we'll have to have a big switch instruction that that looks at the operation and determines, oh, this is an I instruction, and then it hands off control to the assembler that assembles I instructions. So what we'll do is we'll say switch operation, And then if the instruction is an add I, then we want to say assemble I instruction. We pass in the operation. Well, actually, here we need to do a little bit of translation, because add I is just a number that we have for convenience, but when we are encoding the instruction, we actually have to use the opcode for add I. So here is the main opcode for add I, which is this number. Also, we'll pass it in to here. And then we also have to specify the secondary function group, function 3, which are these 3 bits. And then we need to pass in the 3 parameters that were passed, that were used for the destination, the source 1, and the source 2. So in this case, the destination will be passed in just as is, the source 1 will be passed in as is, and source 2 will be passed in as is. And then we break. So I'll remove these 2 instructions or statements now because they're no longer useful. And here then in our new function as am I, we take our, now this is an opcode, and now I want to start treating these fields as unsigned numbers, because I don't want to end up in situations where these 7 bits get sign extended accidentally. I am going to treat them as unsigned numbers, and this is going to be the opcode. And then we'll have another unsigned integer, which is the the func3, and then the destination. We can still use an integer for this. Destination, integer source, and then source 2. Okay, so now we get to assemble this word. So we know that the opcode is supposed to be at the bottom, the least significant part of the instruction. So it is already in the correct position. So we'll start by creating a variable for the instruction, and we'll just slap in the opcode just like this. But then we need to put in the function 3, and the function 3 is at position, bit position 12. So we need to take the instruction and then use bitwise OR to put this function 3 shifted to the right by 12 bits. Okay, so now we have the instruction. And then the destination in add I is in bit position 7. So, and it is a bit field of 5 bits, so we should mask it to 5 bits. And 5 bits is 0B, 1, 2, 3, 4, 5. So we'll take the destination and mask it to 5 bits. And then we'll force that to be an unsigned integer. And then we'll shift it to the right by 7. And then we OR that into our instruction. Then for RS1, that's at bit position 15. So we'll do the same thing here, except this number is changed to 15. And finally, the immediate number in add I is the 11 bits, and they need to be moved up to position 20. So we'll take our SRC2, and this time we're going to mask it by 11. Well, turns out we don't actually have to mask it because any extra bits will just be shifted out of the word. So we're not going to worry about masking SRC2, but we will shift it to to bit position 20 or 20. Bit position 20. So now we should have in the uinster instruction the correct encoding for an I class Risc-V instruction. So now we need to write this to memory. And it turns out that the assembler needs to know or keep track of where in memory the next instruction needs to be written. This is going to be very similar to the emulator, which keeps track of where in memory the next instruction is to be fetched. So what we need to do is introduce a member variable called, we'll call it instruction pointer, and we'll initialize it to 0 initially. And we'll get rid of this constructor actually, because we're no longer using this list of instructions. We'll say this dot instruction pointer equals 0. And now that we have this word, we should now be able to write it to memory. So we'll take our memory and we'll say write little endian word 32. Remember that the Risc-V CPU prefers data in little endian format, and we'll give it the U instruction. And now we get an error because we haven't said where in memory we want this to be written. So we need to give it an address, and that's going to be the instruction pointer. But now there's a problem because when we wrote this method, we were treating addresses as signed integers, and turns out that it's more appropriate to treat addresses as unsigned integers. So what we'll do is we'll change this to become unsigned. Let's change them all while we're here. And then also we will want to be able to write both signed and unsigned values into memory. So we'll just make our life easy here by allowing ourselves to accept an unsigned value and then using the same like this. Okay, so that will write a word into memory, but then after we've written the word into memory, we need to increment our instruction pointer so that it points to the next instruction. Before we in the emulator we incremented by 1, but in this case we actually have to increment it by 4 because it's actually a pointer to a memory address. And since every instruction is 32 bits, which corresponds to 4 bytes, after we write this word, we need to increment it by 4. So let's do that. Okay, so now we've assembled an I instruction. So now we're done. We no longer need this. And I'm not sure, this looks like garbage. We'll discard it. Alright, so there's our first instruction. Let's also add some error handling here. So if it's an unknown instruction, we need to warn the user. For now, we'll just throw an exception. We'll say unknown instruction, and then the name of or the number of the instruction. Okay, so now the assembler has assembled one word. Now we need to take a look on the other side. So the emulator now. So the emulator no longer has a list of instructions to read. It instead has a chunk of memory and an instruction pointer. And so what we need to do is keep this logic, but instead of looking at program, we're going to check the end of memory. So we'll say memory dot well, let's have a method on memory that says is valid address. So if I have an instruction pointer and it's still valid, then we will continue executing. If we end up trying to execute instructions outside of the memory addresses that are valid, then we stop. So we need to implement this method, and is valid address is pretty simple to implement. We'll just say that we return true if the pointer is between these two. So either the pointer is larger than or equal to, well, it's both larger than or equal to 0, and it also has to be less than the length of the array of bytes. So then we need to change the type of the instruction pointer to unsigned, because remember, we're going to treat all addresses as unsigned numbers. And now instead of reading an fully decoded instruction out of a list of instructions, we're going to actually have to read a word out of memory. So we'll say memory read little endian word, and we will return a word, and we'll probably want to change that to be an unsigned integer. Let's see here. Yes, so this is because the C# compiler treats these intermediate results as integers and not as unsigned integers. So by adding those casts, we force the result to be unsigned at all times. Okay, great. So now we have the emulator has read a word, and now we're going to feed it off to exec. And exec no longer takes an instruction, it takes an unsigned integer, which is the encoded instruction. And now comes the challenge. We have to take a look at the instruction and pick it apart into its constituent pieces to make sense of it. So the most important the most important piece of the instruction is going to be the opcode part, the 7 least significant bits. And so what we want to do is extract those 7 bits and then do a big switch statement on those 7 bits. And depending on the value that we find, we dispatch to one of these different instructions. So let's I will leave this, and we'll change the instruction pointer to point to 4, increment by 4. Remember that our instructions are now 4 bytes wide, so we have to step by 4 each time. And then we have to extract the opcode. So let's use that bit field class that we defined last time to create a bit field for the opcode. So we'll say private static bit field opcode, and this is the bit field that starts at position 0 and is 7 bits long. Nice. And then what we want to do is read the opcode. So we'll say var opcode equals bit field opcode, and then extract, and we pass in the instruction. But notice again that the bit field expects an assigned integer. So we'll create a different version of extract that takes a unsigned integer and then returns an unsigned integer like this. And then we'll have to change the mask and the computation of the mask. I guess we'll discard this. We're no longer using this anywhere, so we can safely get rid of it. And so here is our unsigned version of the extract. I'm going to call this extract unsigned because we'll shortly need a signed variant of this. So let's go back now to the emulator, and now that we have the opcode, we can now do a switch on the opcode. Okay, so in this case, add I is down here. This is the instruction that we need to recognize. So what we can do is we can say, if the opcode is this, then it's an add I instruction. And in the case of an add I instruction, we need to extract the funct3 field, because we want to distinguish this from the slti instruction, which has a funct3 of 0, 1, 0. So we have to create another bit field, and this bit field is the bit field for position 12, and it's 3 bits wide, and we're going to call it funct3. And let's find our, here it is. So here we have to say then funct3 is bit field funct3 extract unsigned. Nice. So now we can do a second switch on funct3. And in the case of 0b000, we now want to execute the add I instruction. So we need to extract fields for the source and then the immediate number, which is encoded in the most significant 11 bits, 12 bits. So, and what we can do then is steal the already existing implementation of add I from this, and we'll put it in here. And we can add this as a comment. And so instead of fetching, well, we don't have an inster, we have to fetch src1, so we'll create another bit field for src1, which is going to be here, and src1 is bit 15, and it's 5 bits wide. So bit field 15, 5 bits wide. And we might as well do the destination, which is bit 7, also that 5 bits wide. And finally we have this immediate field that starts at bit 20 and is 12 bits wide. So we'll have private static bit field, and we'll call it im20 because it's the one that is at bit position 20, and then that will be 20 and length 12. 20 plus 12 equals 32, so that's nice. It is correct. So now what we can do is we can say that we'll create a few variables here also. We'll have an unsigned source1, an unsized destination, and then a signed source2, or im. Okay, so let's extract source1. So source1 is going to be bit field source1, extract unsigned, and then we're going to grab that from our instruction. And then our immediate is going to be bit field source, or immediate 20 extract. And now we want to extract that number as a signed value. So here we have to do a bit of trickery, because the number as it is now is unsigned, and we want to convert it to a signed value. So how do we do that? Well, there are some tricks that we can use. What we can do is the following. We first extract the bit, shifting it to the right, and then masking it. So now the result is in unsigned format, but shifted all the way to the right. We'll call that the... Well, actually, just let's cast it to an integer already. So now what we'll do is we'll take that packet of bits and shift it all the way to the left. So we'll do that by taking n and shifting it to the left by 32 minus... we need the bit width to do this correctly. So let's hang on to the bit width in our bit field. That's the ticket. So what happens now is that this little packet in n are bit width. There are bit width number of bits in n. We're going to shift them all the way to the left, so that the most significant bit in the bit width chunk is going to be at bit position 32. And then we're going to shift it all the way back. And remember that when we have a signed integer like n and we shift it to the right, if the highest bit position of n is a 1, then that 1 gets replicated, thus extending the sign of the number. And this results in a sign extension, which is exactly what we want to happen. So let's put a bunch of parentheses here, and then let's store it like this. We need to cast that. Now there are more efficient ways of doing this sign extraction, but for now I'm happy that this should work correctly. Once we get it to work, then we make it fast. Okay, so we have now an extract sign method, and now we can use that extract sign method to extract the immediate value. Now we actually perform the computation. So we take the... Oh, we actually need a destination. So we have to say bf destination. Okay, here we go. So now we finally can take these numbers and perform the computation. So add I is implemented as grab the value inside of the source register that's specified in src1, add the immediate value, and then store that back into the destination. Okay, this is the only instruction that we know so far, so if there are any others, we should throw an exception. We'll say unknown major opcode, and then our major opcode is this opcode in base 2. And then here, similarly, we'll have so this should catch any unimplemented instructions. For now, we'll just comment out these remaining ones because we are not in a position to handle them quite yet. We have to get all the infrastructure working before we can finish all of the instructions. Okay, so what exec is supposed to return now is the new instruction pointer. I'll make that unsigned. And what else? Yes, we need to return. Like so. Oh, still unhappy. Why are you unhappy? I forgot a curly brace. There we go. All right. So let's build this and see what happens. Oh, we're missing something. Okay, what is going on here? The exec function is balanced, but the class is not. Okay, that fixes that. And then, yes, this assembler will no longer work. So we'll just discard it. Now we'll try building again. Okay. So now, in theory at least, this should work. We're expecting to read the assemble instruction add I out of memory, and then it's supposed to execute, taking the register value, which is in R0, or X0, which is always 0, add 42 to it, resulting in a value that gets stored in register 2. And then we'll confirm that indeed the value that we read out of register 2 is 42. So let's try running this. And it's unlikely that it will work the first time, but it's always fun to test and see whether we're lucky enough. So here we go. And there's a failure. The failure is this instruction right here. Okay. So I'd like to see the actual failure though. What unknown major opcode 0. So there's a problem already. We don't seem to be disassembling the word correctly. So we'll have to debug this now. It's painful, but the very first instruction is always going to be painful. Once we figured out all the glitches, most of the remaining instructions will be easy enough to add. So let's go and take a look at the assembler first to make sure that the assembler is actually getting invoked and that we are actually writing the correct value to memory. So let's run our test under the debugger. And here we go. So the operation is 1, which is add I. So we should enter the correct case in here. And the destination is 2, source register is 0, and the value is 42, as expected. Okay, so now we're going to build our word that we're supposed to write. And if we look at this instruction, hard to tell, but this is likely correct. We're taking the function, shifting it by 12, and ORing it all in. So all of this does look good. And then we write it to memory. Now inside the memory object, we should see those a bunch of bytes being written. This corresponds to the data that we the instruction treated now as data. And then we skip to the next address, which is correct. And then we're done, and we leave. Great. So that was that. So now we have assembled our little program, and then we're going to tell the emulator, please start executing our program. And so we're going to read a valid word, which is this instruction right here. And that looks like the same value that we wrote before. So then we're going to go into the exec instruction. And we're going to grab the principal opcode. And the opcode is 19, so that's correct. And then we're going to grab the funct3 field, which should be 0. It is 0. So we successfully... yes. Okay, so this does work correctly, but then after this switch statement, no, we do return. And now I pointer should be 4, correct? And so this should now fail because we're now out. Oh, we are still inside of memory. Okay, okay. So we are now executing the next 4-byte word, which is a bunch of zeros. And that is an invalid instruction in Risc-V. And so we crash and burn. Okay, great. So what we'll do is we'll add a handler for the case when the instruction is 0 for the time being to just stop execution. So what we'll do is we'll say if the instruction is 0, then break. And this is not strictly correct because the Risc-V specification specifies something different when you execute an instruction that is a 0. But for now, we're going to use that as a signal for us to stop executing our program. So let's give that another try. And there are a few things more beautiful than getting that green dot, letting you know that your unit tests have passed. So we now finally are emulating actual Risc-V instructions. Well, 1 to be more precise. But this instruction that we not only are emulating but also assembling would execute on any Risc-V core and produce the same result. So that concludes this session. And in the next session, we're going to start adding some more instructions to get to the point where we're able to compute the factorial function. After that, we're going to start talking about more advanced assembly language topics. I hope you've enjoyed this, and see you next time.